Kirkwood Math. All right, ladies and gentlemen, we are here on 8.5. This is the last of our topic 8 lessons that we're going to do. We're looking at systems of equations with special cases. Okay, so you're taking notes on your screen here. Now, I know that you might not have a lot of room in your notes, but you're going to try your best. You might need to use the back or on the side of your notebook because we've got some important information coming at you. So the first thing we need to know is that the one solution, so these are the words that you're writing down in your notes. One solution, no solution, and infinite solutions. This should sound familiar because we talked about these before when we were solving just one equation. But now we have 2 equations that we're looking at, and so we're going to look and compare what does it mean when I get certain things. When do I have just one solution? When do I have none? And when do I have an infinite amount of solutions? So one solution is the most common that you're going to see. It's when the 2 lines intersect, okay? So when the 2 lines intersect. Okay, you're going to see if I was solving this algebraically, like using substitution, I would get just an answer, a normal answer, like y equals 0, x equals -2. Okay, if I'm looking at their equations, the equations of these lines, which are y equals -x minus 2 and y equals positive x plus 1.5, you might notice that the slope and the y-intercepts are different, okay? So when looking at the equations, your slope is different. It actually doesn't matter if you have different y-intercepts because you could have your intersection be on the y-axis. As long as your slopes are different, you have one solution. So no matter, there are about 3 different ways, probably more, that you can solve these problems by looking at a graph or by graphing them. If they intersect in one spot, that's one solution. I can solve them using substitution. If I get an answer like y equals blank or x equals blank, that's one solution. Or by looking at their equations in slope-intercept form, if they have different slopes, it's one solution. Okay, so now we're going to go ahead and look at what it means to have no solution. So you probably noticed that no solution lines are parallel. It means that they do not touch, right? They are railroad tracks. They continue forever and ever and ever in the same direction, and they're never going to cross. That's why we have no solution, because they're never touching. Okay, if I solve it algebraically using substitution, I'm going to get something weird like 5 equals 6, which is not true. It's untrue. Okay, if you get an untrue statement when solving algebraically, then you should know that's no solution. Then if I look at their equations, and these equations are y equals x plus 1.5, y equals x plus, I think it's 6. You might notice that their slopes are the same. So if you have the same slope but different y-intercepts, it's no solution. Same slope, different y-intercept. Okay? All of these, no matter which way you're solving it, mean no solution. And then the last one we're going to look at is our infinite solutions. So for infinite solutions, you probably notice that they are touching infinitely. They are the same line. So if I look at a graph and they are on top of each other, they are the same line, I know it's infinite solutions. If I look at their equations and they are the same equations, then I know that it is infinite solutions. This one is going to be -x plus 1, we'll say. So notice that in this one, I have the same slope and the same y-intercept. So when I have the same of both, and y-intercept. Then I know that it's infinite solutions. And if I'm solving this algebraically, instead of getting an untrue statement, I would get a true statement like, for example, 6 is equal to 6, or 12 is equal to 12, as long as whatever's on the left is equal to or is the same as whatever's on the right, it's going to be infinite solutions. So let's try this out. Okay, so we're going to do this 2 different ways. I'm going to show you, technically 3 different ways, but for method 1, we're going to do substitution so that you can see how to solve this. Now, you don't need to do this normally 3 different ways. I'm doing this to help show you all the ways that you can go about doing this problem. It is up to you which one is easiest for you. I would say if you know that it is a special case situation and they say something like, what's the type of solution? I would go by graphing or rewriting in slope-intercept form. If you don't know if there's one solution or infinite or many, and they want you to actually give the answer if it's one solution, then you can pick any way because you're not going to know, and most likely it's going to be one solution. Okay, so with substitution, I'm going to identify my smart variable, which in this case, I'm just going to pick x, and I'm going to rewrite my equation isolating x. So I'm going to add y to both sides. Whoops. And I'm going to get y minus 2. I now know that x is the same as y minus 2. So when I go back into my equation over here, I'm going to replace this, my other equation, substitute y minus 2 for x, because x is the same as y minus 2. So I'm going to go ahead and say, okay, minus y minus 2 plus y equals 4. And I'm going to go ahead and solve this problem. So I'm going to distribute this negative, because remember, it's really a negative 1. So negative 1 times y is negative y. Negative 1 minus 2 is positive 2. Okay, I am now going to combine my like terms. So you may have noticed I've got 2 y's here. We're going to combine those together. But when I combine these together, what's a negative 1y plus 1y? Well, that makes 0y or just 0. They cancel out. And I'm left with 2 equals 4. Now go back to the previous page and take a look. What does it mean when I have something that is untrue? 2 does not equal 4. You should be saying, no solution, no solution. You're right. So by using method 1, I was able to figure out this is a no solution problem. What we're going to do now is go ahead and go to graphing and use method 2. And we're going to graph. Okay, and I'm going to show you. So again, these are 2 separate methods. You do not need to do both of them when solving. I'm just showing you 2 different ways to do it because you might have still be struggling with substitution, and graphing might be more of your stronger suit. So I'm going to take both of my equations and I'm going to rewrite them in slope-intercept form. Okay, so I'm going to isolate y. I'm going to subtract x on both sides. Okay, I have a negative y, which isn't good, so I'm going to multiply everything. Oopsie, I did a positive 2 instead of a minus 2. I'm going to multiply everything by a negative 1 in order to get rid of my signs, my negative signs, and turn them positive. I'm going to rewrite it over here. I'm going to have y equals x plus 2. So that is going to be my first equation. Okay, and I'm not going to graph them yet. We're going to just stick over here with solving. So now I'm going to isolate y over here by adding x, oopsie, to both sides. There we go. This is going to cancel out. And I'm going to be left with y equals x plus 4. So that's my second equation. Now, before I even graph them, because I could graph, that's actually kind of method 3. Before I even graph them, if you go back to your previous page where we took notes, if you look at the slopes of these 2 equations in the y-intercepts, you'll notice that the slopes are the same, but the y-intercepts are different. And if you go back to our notes, you'll notice that that means no solution. So before I even graph it, I can just look at my two equations, change them into slope-intercept form, and compare. Now, if you are still struggling with that, if you don't remember which one's which, the final thing, the final kind of method you can do that we're learning about is to graph those lines. So the last thing I'm going to do, we're going to say it's method number 3. Is now to take those lines and graph them. You can also graph them to just check your work and make sure that you are correct. It's always hard to draw a straight line on my computer here, so I'm going to do the best I can. And then my other line here is at +4. There you go. Now when I graph my two lines, you should be able to clearly see that they are parallel, and we know that parallel lines have no solution. Okay, so those are 3 different ways that I can solve this problem. It's up to you which one you use. You can use the same way every time. You can change it up based on the problem. You kind of have to pick what's easiest for you. Like I said before, though, if it tells you, like if the question is, what type of solution is this problem, I would probably use this graphing or looking at changing my equations into slope-intercept form method, because you're going to be able to see pretty quickly through these equations if it's a 1, none, or infinite. If you have to find a solution, it's up to you, because I could graph, but sometimes if I have decimals in my answer, it's not going to be 100% accurate. It's going to be an estimate. Substitution would be more accurate. Okay, so on this problem, we're going to just do that method I told you that, because we know that we're looking for special cases. I'm just going to change them to slope-intercept form. And I'm going to see what it equals. So I'm going to have 2x plus y equals -2. I'm going to subtract 2x on both sides, and I'll get y equals -2x minus 2. So that's my first equation. And I can compare these, okay? My second equation is 4x plus 2y equals -4. I'm going to subtract 4x on both sides, and I'm going to get 2y equals -4x minus 4. But I'm not done yet, because there is a coefficient in front of y. I don't want a 2 there. I want it to have nothing. So I'm going to divide everything by 2 and get y equals -2x minus 2. So that is my second equation. So now I can compare my two equations. So if I look at these two equations here, you'll notice that they're exactly the same, which means that it's infinite. So then to check my work, I can always graph it, but we know that it's the same equation. 1, 2, -2, doop, doop, doop. So I'm going to get the same line, one on top of each other, right there. Okay, so go ahead and practice on this. These 3 right here, remember that when it says tell how many solutions each system has, or when it says what type of solutions are there, I'm probably just going to rearrange these into slope-intercept form. So that's what I recommend you do. If you prefer to graph, there is a graph on your paper. Or no, you can get graph paper and graph. If you prefer to do to do substitution, then do substitution. But go ahead and practice that and then come back and check your work. All right, so here are your answers if you are solving them. So I rearranged all of my problems into slope-intercept form. On this guy right here, you can see that they have the same slope but different y-intercepts, so it's no solution. On number 7, we have completely different slopes and y-intercepts, so it's 1 solution. And on number 8, they end up being the identical same equation, so it is infinite. And so the last thing you're going to do is go ahead and try this independent practice. See if you can figure out the number of solutions in these systems that are described below. So a system whose graphs have the same slope but different y-intercepts, go ahead and look that up. What is it? No solution. Okay, a system whose graphs have the same y-intercepts but different slopes. Anytime they're different slopes, that's your keyword there. It's going to be 1 solution. Okay, and that's all we've got.